Thanks. We're going to shift gears a little bit now away from VOCs, although I'll come back at the end and talk a little bit about VOCs in these regions as well. We're also going to move back north, looking at the Jonah Pinedale area and the Bakken region. And we're going to focus on winter fine particle formation in haze episodes. I'd like to acknowledge my co-authors from Colorado State, from the Park Service, from Air Resource Specialists, and from Shell. This work was funded by Shell in the Jonah Pinedale area and from the National Park Service in the Bakken. So if you take a look back over the last decade or so, you can see that the U.S. has made a lot of progress in reducing concentrations of fine particles tied to reductions in NOx and SOx emissions across much of the country. For example, this analysis by Jenny Hand shows reductions up to several percent per year averaged over this time period in nitrate concentrations. This particular plot is for the month of March. And what you'll notice if you look at several months during the winter time, not all parts of the country share in this benefit. Some regions show little decrease or potentially even increases. And as you look at different months, this tends to be mostly sort of the interior western part of the United States. And so there's interest, of course, in why this region looks different. And one possible hypothesis is that the emissions from increased oil and gas in this region are offsetting the reductions that may be occurring from power plants and motor vehicles and other sources. So for example, we've already heard about the Bakken earlier this morning. If you take a look at this nighttime VIRS satellite, it looks like a big city up here in western North Dakota. Trust me, there aren't very many people there. But there's a lot of oil activity, and you can see this ramp up in production in the late 2000s, North Dakota now being the second largest producer of oil in the U.S. So this may be a source of NOx. It's important for nitrate production, but of course in the winter to get nitrogen into the fine particles, we need not only nitric acid, which can come from NOx oxidation, but we also need ammonia to react with that. And because ammonia is not yet at least a regulated pollutant, we tend not to know very much about its spatial or temporal variability. So we're going to take a look at two different regions where we've been looking at this situation for wintertime ammonium nitrate formation. We'll start in the western part of Wyoming in the Jonah Pinedale region. Here we've been working since late 2006. Making measurements with denuder filter packs around the year of things like ammonia, nitric acid, and sulfur species, as well as the other nitrogen fine particle species. As you heard earlier this morning, this is one of the largest gas-producing regions in the U.S. Shell was interested in ammonia in this region because their assessed visibility impacts based on reactions of their NOx oxidation products with background ammonia. So I'm going to simply show you for this region some seasonal timelines of nitrogen species concentrations here. So these start in 2007 and go up through the end of 2013. If we start on the bottom panel, you can see the reduced nitrogen concentrations. The dark green line is the fine particle ammonium. You notice that doesn't have a very strong seasonal pattern, a bit of one. But if you look at the lighter green, that's the gas phase ammonia. And there we see a very strong seasonal cycle with the peak in the summertime each year. Now this isn't surprising. We expect ammonia emissions to go up in the summertime. We also believe that long-range transport of ammonia from other source regions is more productive at this time of year. If you look at the top, we see something a little bit more surprising. This is the oxidized nitrogen timelines. So not so surprisingly, we see the fine particle nitrate peaking in the winter time. What is more surprising is that you see also a winter peak in gas phase nitric acid. Normally expect nitric acid to end up in fine particles in the winter, but if you take a look at what's happening during these peaks in nitric acid, we've essentially titrated all the ammonia out of the gas phase. So there simply isn't very much ammonia around in the winter here to react with the nitric acid. The nitric acid is being produced in the same winter photochemistry that's producing the high ozone in this region. But it's essentially stuck in the gas phase. So we limit, because of the limited amount of ammonia, the total amount of fine particle nitrate. And these are 3 and 4 day samples throughout this period, and you see we tend to reach averages only around a couple of micrograms per cubic meter over that time scale. Well, let's contrast that with what we've been looking at more recently in the Bakken. So again, now we're up here in western North Dakota. Here's the North Dakota-Montana state line. This shaded region, these are the oil wells in the Bakken Formation that have been developed. There are some other important sources up here, for example, these coal-fired power plants. And we also have been making measurements here in early 2013 and then in winter 2013 and 14 at some combination in each of those years of these 5 colored sites. Our core site is in the north unit of Theodore Roosevelt National Park. The Park Service is interested about visibility impacts from development in this park. I'll also show you a fair amount of data from Fort Union, and you'll notice both of those are sort of in the heart of this oil well production region. So again, let's start just with timelines, and we're going to start with early 2013. The panels here are the 4 different sites where we had daily or 48-hour measurements, and the stacked colors are simply sulfate, nitrate, and ammonium are the ones you can see. There's some other species that are much smaller here. What I want you to notice is that when we see an episode of high particles, for example, in this north unit, we tend to see that across the different sites. And we can pick out sort of regional episodes where we get accumulation of this fine particles and haze across the basin. If you look, for example, at Fort Union, that's where we saw the highest concentrations in early 2013, with ammonium nitrate reaching about 15 micrograms per cubic meter over a 48-hour average sample. So, of course, it's interesting to wonder what ammonia availability looks like in this region. Why isn't ammonia limiting the nitrate formation here like it was in western Wyoming? And I've plotted here the fraction of ammonia in the gas phase, just as a function of time. The top red line is Fort Union, the one with those highest concentrations, and the purple line is Theodore Roosevelt National Park North Unit. And what you can see during these 2 episodes, which I've highlighted here, is that sometimes, for example, here at the park, we're getting down where we have less than 10% of the ammonia left in the gas phase, but we still have 20, 30%, something like that at Fort Union. And in this episode, as we move a little bit further, I shouldn't say into spring, it's still really winter up here at this time of year, but we have at both sites a fair amount of ammonia still available in the gas phase. So that ammonia is sufficient to allow these high nitrate formation episodes to take place, and even there's some potential for more if we had more nitric acid around. We moved this year back up there, and we did a lot more detailed measurements, including a lot of VOC speciation. We did more continuous measurements, but for consistency, I just want to show you these timelines again of the 24-hour measurements and draw your attention to the fact that, again, we're seeing these episodes. Sometimes there's a fair amount of sulfate in these episodes. Sometimes they're more nitrate dominated, but again, they tend to occur across sites. The other thing I want to point out is that in this winter, the peak concentrations, for example, nitrate here is only on the order of 5 micrograms per cubic meter, so quite a bit lower than we saw in the prior winter. But we can look again at the ammonia availability in this situation, and if we focus on those episodes, this is now just for Fort Union. The gas phase ammonia is in the green dashed line, and you can see we come close to depleting most of it in these episodes, but in this episode we still have about 60% or so of the ammonia in the gas phase. So for reasons we don't fully understand yet, although it's winter, there's snow on the ground, there's quite a bit more ammonia available in this region than we're seeing in western Wyoming that's allowing these episodes to become more severe than we see in that other basin. Now, why do we get these episodes? Well, it turns out to be fairly simple. We, of course, have a lot of emissions going on there. Most of the time, the wind is blowing. It's cold and windy. It's fairly flat, and the wind is often coming strong out of the west or northwest. And when that happens, we see fairly low concentrations. But when we get periods of stagnation or recirculation, for example, as highlighted in these 2 examples, is when we get this rapid buildup of fine particle concentrations. In the poster session this afternoon, Barclay Sive is presenting some of the analysis from the VOCs. that were collected in this environment. These are from this past winter, 2013-14. I'll just highlight two examples here for you. The first of these is the ratio across the 3 sites where we're making these measurements across the basin of I to N pentane. You see that ratio follows very tightly, about 0.76. This is definitely indicating a strong oil and gas influences versus an urban influence. Not that there's a huge urban area up there, but there is some population and it's growing associated with this activity. The other thing that Berkeley has been looking at is putting a chemical clock in terms of the age of the VOCs that we're seeing. So we're seeing oil and gas VOCs at the site when we're getting these PM episodes. And if you look at the age measured in terms of the formation of alkyl nitrates, we find that the time scale, the lifetime of the VOCs when we're getting peak PM episodes, as illustrated by this scale, is on the order of maybe a half a day to a day. So once the wind stops blowing or starts recirculating, we get this fairly rapid aging that's producing some of these fine particle episodes. It would have been quite interesting to have these kind of data in the bigger episodes we saw in 2013, but unfortunately we didn't during that time. So let me conclude by just saying that in both of these environments, by fraction, ammonium nitrate is an important component of winter haze. It's certainly of concern in both regions. But what we find in the Jonah Pinedale region is that the low ammonia availability limits the peak concentrations of ammonium nitrate that are generated there, and nitric acid ends up stuck in the gas phase. In the Bakken, there is more abundant ammonia, and again, we don't fully understand why. It's so much more abundant in that environment, and that supports greater PM nitrate formation. And the VOC signatures certainly indicate during these haze episodes that we have a strong local contribution from oil and gas. And in particular, if you're interested in the work in the Bakken, I'd encourage you to go see Berkeley's poster this afternoon and another one by Arsina Hakobian looking at some mobile measurements both of methane and VOCs in these regions. Thank you.
We have a few minutes for questions. Questions?
Was the sulfate always fully neutralized in the Pinedale area?
In Pinedale, it's a while since I looked at that. Not in the summer always. Well, no, it generally was neutralized there. There are a few episodes where it is not, but most of the time it is. We looked at some of those episodes. They look like they're maybe very long-range transport where we don't have much ammonia. But on average, it's neutralized.
In the wintertime, too?
Most of the time. At least averaged over these time scales, which are 3 to 4 day samples.
Yeah, you won't be able to form ammonium nitrate unless you fully neutralize the sulfate.
Yes.
Not any more questions.
Do you have a sense of what the source of ammonia is?
Yeah, that's a good question. And we tried to make some mobile measurements this winter of ammonia, but we had some issues with power on the mobile lab doing that, just to see if there's a clear spatial pattern. We have heard in the eastern part of Montana that farmers sometimes will put fertilizer down onto snow because they think it reduces the loss of that. We do definitely see ammonia start to come up as we move into sort of the March timeframe. It's quite a bit lower in, say, January, like we would expect, but at the shoulders of the winter, it's a bit higher. It's possible there's some other sources associated with, for example, NOx control on vehicles or something operating at very cold temperatures. We don't know. It's definitely closer to some agricultural regions to the south. And during 2013, there was some suggestion that we got more ammonia when we had transport from the southeast. This last winter, we didn't have much transport from that direction, so it's a little bit different.